Alright, so I'm going to play around with some Cuisenaire rods. We're going to do some interesting stuff. So the first thing I'm going to do is I'm going to mess around with triangular numbers. Now triangular numbers are from time of Pythagoras, and they're just taking 1 and then adding 2, and then adding 3, and adding 4, and so on. You go 1 plus 2 plus 3 plus 4. So a triangular number would be T1 is just 1, because that's the first one. T2 would be 1 plus 2, which is 3. T3 is equal to 1 plus 2 plus 3, which is 6. T4 is 1 plus 2 plus 3 plus 4, which is 10, like that. Just like 10-pin bowling. So those are triangular numbers. So if I wanted to find out what any number of them would add up to, it'd be nice to have a formula. And so what I could do is something like Tn is 1 plus 2 plus 3 plus up to the nth 1. Now what would the sum of that be? Well, here's a cool little trick we'll do. I'm going to take this triangular number. We'll just do it with this one just to show you. And it generalizes to all the sizes. Now if I take another triangular number and put it together like this, put 3 here so they all add up to 5, right? Oops, I need a 2, and I need a 1 here. Alright, so notice that I have 2 triangular numbers, 1 plus 2 plus 3 plus 4, 1 plus 2 plus 3 plus 4. And they add up to a rectangle, right? A rectangle that is 5 along here, because that's 4 and 1, and then 1, 2, 3, 4 there. So notice that if I take T4 plus T4, I get 4 times 5, like that. Well, if I did this with it and generalized it, I would get Tn plus Tn is equal to n, and then of course that's the same, and then that one's 1 bigger, n plus 1. Now because there's 2 of them, I can divide both of them by a half, and I get Tn is equal to Tn n plus 1. And now we have our formula of what this thing is. This would be n times n plus 1 over 2, and we have our formula for the triangular numbers. Alright, so now we're going to try another type of number, the square number, right? So we have 1 squared, right? 1 times 1. And then if I take 2, I would have, this is 2 this way and 2 that way, 2 squared, which is 4. These are easy enough. Then we get 3, right? 3 this way, 3 that way. 3 squared is 9. And then if I take 4, I get 4 squared, which is 16, right? Square numbers. But could I create them another way? Well, what if I took 1 and then I broke up, I could notice that I could break this one up into 1 and then like that. So that would be 3. And I would get that this is, well, this one's still just 1, but this would be 1 plus 3, which is 4. Now if I took this one, let's slide it over here, so I have that one. And now if I take 3 of these, and I put a 2 in here, notice that then I have 1, 3, and that's 2 plus 3, that's 5, and I get a perfect square again. So this is 1 plus 2 plus 3, or sorry, 3 plus 5, 1, this is 1 plus 3 plus 5, which gives me a perfect square. That matches up exactly with a 3 by 3. putting it on top like that. Alright, and then of course this one, right? Could I build it the same way? Sure I could, because I could take 1, and then there's my 3 I made, and then there's my 5 that I made, 1 plus 3 plus 5, and then of course I have 3 and 4, which is 7. So I have 1, 3, 5, and 7. This is 1 plus 3 plus 5 plus 7, which is 4 squared. This one's 3 squared, and this is 2 squared. So notice that what's happening is the number of odd numbers I have adds up to be exactly the thing that's being squared. So let's make these odd numbers out of this. How do we make an odd number? Well, we know we can make an even number by doubling it, right? So if I make 2, I can take 1 away. If I make so 2, take 1 away, gives me an odd one. If I make a 4, and I take 1 away, I get a 3, right? So I'm always going to get an odd one. So if I took this 1, 2 times 1 minus 1 gives me 1. 2 times 2 minus 1 gives me 3. Here, if I took these, 2 times 1 minus 1 equals 1. 2 times 2 minus 1 equals 3. 2 times 3 minus 1 equals 5. And I bet if I do the same thing here, 2 times 1 minus 1 equals 1. 2 times 2 minus 1 equals 3. 2 times 3 minus 1 equals 5. 2 times 4 minus 1 equals 7. So notice that what's happening here, 1, 2, 3, 4, 1, 2, 3, 1, 2, is that how many numbers I have is this one right here. So odd numbers, I could go 1 plus 3 plus 5 plus how many odd numbers I have, 2n minus 1, because the n is how many odd ones. That one has to be n squared. And so I have this formula. If I sum the first n odd numbers, which is what this says, I would get n squared. Alright. So let's try another one that's kind of interesting. And so let me quick build this. Alright, so I have to pretend these are 4s because I ran out. So notice that there's something interesting happening here. If I go along and count the bottom, I have 1, 2, 1, 2, 3, which I could have put the other way. Probably should have flipped those. And 1, 2, 3, 4. Same here. 1, 2, 1, 2, 3, and a 4, right? So if I want to think of this squares, how many cubes I have, I would have 1 plus 2 plus 3 plus 4. That's a side, and then the other side, that's a square. So I get something that looks like that. Now what I'm going to do is I'm going to rearrange these and see if I can get a formula out of this. So what I'm going to do is I have a 1, that's a cube. Now notice that if I stack these like this, that makes 2 by 2 by 2. Let me slide these down, put those there. So out of the 2's, I can get a 2. So I have a 1 cubed and a 2 cubed, like that. Now I'm going to take the 3's, and I'm going to take my 3's and build these up. Notice that I can make those into a 3 cubed. And now the 4's, which I have to pretend these are 4's, right? So let's make that our base. And then I take 4 of them, and I lay them down like this. I take another 4 of them that I have, I lay them down like that. Then I take my last 4, and I get my wonky but 4 by 4 by 4. So I get that this is 4 cubed. So I have a 1 cube, a 1 by 1 by 1, a 2 by 2 by 2, a 3 by 3 by 3, and a 4 by 4 by 4. And I get this cool little formula here by Nicomachus. And so this is kind of interesting, because if I generalize it like I did with the other ones, right, this would say this is the sum of cubes. So that would be 1 cubed plus 2 cubed plus 3 cubed plus up to n cubed. Now if I look at what I have here, this is a triangular number. Now we know that the sum of triangular numbers is, so inside the parentheses, this is the n plus 1 over 2 squared. And we have this theorem by Nicomachus, ancient Greek, the sum of the cubes. So our interesting 3 results that we had made up, we had the sum of the triangular numbers, which is the sum of the first n integers, so using it in more modern notation, we get this. We had the sum of odd integers was n squared. And now we have this one, which is the sum of the first cubes, and we get n plus 1 over 2 squared. And we have our three kind of interesting results. So these colors represent the triangular numbers. 1, 3, which we recognize as 1 plus 2, right? And then 1 plus 2 plus 3 is 6. And then 1 plus 2 plus 3 plus 4 is 10. So there's our triangular numbers like that. So now we're going to do something interesting. So what I'm going to do is I'm going to take 1, 1, 1. And I'm going to take a square, 2 by 2 square. Then I'm going to take a 3 by 3 square, so it'd be 3 3s, and a 4 by 4 square. And I'm going to want to look at, what do I get when I add up how many of these that I have? Well, what I'm going to do is I'm going to look at this. So this one is, so what I have right now, I have, let's see, let's move this up a little higher now, right underneath it. You can see I have 1 squared plus 2 squared plus 3 squared plus 4 squared, like that. And what I'm going to add to it is this. I'm going to add a 1, and then I'm going to add a 3, oops, like that. And if maybe I can add a 1 if I get this in right, like this. And then I'm going to add a 6, and then I'm going to add a 10. So notice that what I'm going to do is I'm going to change my equal sign to a plus. I'm going to add in a 1, a 3, a 6, and a 10. Now, what is that equal to? Well, if I go this way, I have 1 plus 2 plus 3 plus 4. So that's one side of my rectangle. And the other side I have 1 plus 2, 3, 4, 5. So I have 4 plus 1, like that, if I want to add it up, make it look like that. So this kind of is interesting because I have this triangular number and I have a bunch of triangular numbers here. So let's do this. Let's just write this here. 1 squared plus 2 squared plus 3 squared plus 4 squared. Now this thing I'm going to rewrite as 1 times 2 over 2 plus 2 times 3 over 2 plus 3 times 4 over 2 plus 4 times 5 over 2. And then this is going to be 4 times 5 over 2 times 5 again. So let's just make that squared like that. All right. So now this one, if I do this right, I'm going to factor out a half. Let's start off with that first. Let's factor out a half out of that bit right here. So I'm going to factor a half out of this stuff, so I get 1 half. And then I'll notice this. I'm left with 1 times 1 plus 1. Plus, now this one is 2 times 2 plus 1. Plus 3 times 3 plus 1. Plus 4 times 4 plus 1 equals, now this, nothing's changed over here. Now why did I do that? Well, I did that because notice that when I multiply these through now in a different way, I get 1 plus 1 squared. I can write it like this, 1 squared plus 1. So I'm going to write this, keep this the same over here. Right, and now this side I'm going to go leave the 1 half, right? And now I'm going to have, now look at what I'm at here. I'm going to have a 2 squared and a 2, a 3 squared, and a 3. So I'm going to write this like this, 1 squared plus 1 plus 2 squared plus 2 plus 3 squared plus 3 plus 4 squared plus 4 equals all of this same stuff over here. Now that's kind of interesting, because now if I rearrange this, I'm going to get a 1 squared, 2 squared, 3 squared, 4 squared plus. Now I'm going to have 1 half of, now if I regroup the squareds, this would be 1 squared plus 2 squared plus 3 squared plus 4 squared plus 1 half, 1 plus 2 plus 3 plus 4. All right. Now these two I can combine together to give me 3 halves. 1 squared plus 2 squared plus 3 squared plus 4 squared. And now this one I can write as 1 half. And of course that's just 4 times 5 over 2. And this is 4 times 5 squared over 2, because that hasn't changed. All right. So I'm kind of running out of space here, so hold on one sec. Alright, so I'm going to move this over to the other page just because I ran out of space. I have 1 squared, 2 squared, 3 squared, plus 4 squared. And 4 is kind of, I'm using this as my, what I want n to be when I get done to be the end, because there really should be lots of stuff in here, right? And this is 4 times 5 squared over 2. All right, so I want this by itself, and I want to see if I can figure out a good formula. So let's just subtract that other piece over for now. What does that give me? That gives me 4 times 5 squared over 2 minus 4 times 5 over 4. All right, so what should we do with this? If I want to factor out, let's do this. Let's say they all have 4 5s and a 2. So let's factor out a 4, 5, and a 2. And what would that leave me? That would leave me a 5 here. And that'd leave me what would that leave me? 1 half there, I guess. So if I want to get a common denominator with that side, let's try that. That'd give me a 4 times a 5 over 2, and then this would be a 10 minus 1 over 2. Like that. Now, remember the 4 is kind of the important thing here. So how can I write the 10 as a 4 with a 4 in it? Well, I think if I did this off the side, right? If I took 4 and I multiplied it by 2, that would give me an 8. And then if I added 2 to it, that'd give me a 10, like that. So let's plug that in there, because it has a 4 in it. That's kind of the... So I'm going to write this as 4 times 5 over 2, and I'm going to replace the 10 with 2 times 4 plus 2 minus 1 all over 2, like that. Okay. So that, let's just simplify this part. That becomes a plus 1. So I have 4 times 5 times... Now this is... That would be 2 times 4 plus 1 all over 4. So if I rewrote it, let's rewrite the 5 so it looks like it has a 4 in it, because everything's about 4s, and then multiply the 2/3 over. So if I get 1 squared plus 2 squared plus 3 squared plus 4 squared is equal to, multiply this by 2/3, and what would I have? 4 times 4 plus 1 times 2 times 4 plus 1 all over 4. Now the 2 goes into that 2 times, so 2 times 3 is 6. So I get 1 squared plus 2 squared plus 3 squared plus 4 squared is equal to 4 times 4 plus 1 times 2 times 4 plus 1 all over 6. And I think now we have the formula that we're looking for. So if I take 1 squared plus 2 squared plus 3 squared plus ... up to n squared, that's an n. That's an n plus 1. That's a 2n plus 1 all over 6. And I think there we go. We have our formula that we want for the sum of the squares. So in the end, we get the sum of the squares is written in summation notation, more modern. 1 to n of k squared is equal to n times n plus 1 times 2n plus 1 over 6, like that. And we have our sum of the squares formula. So, yeah, with Cuisenaire rods, this is really kind of interesting. And this is actually probably the way the ancient Greeks would have come up with these formulas, is using some sort of calculation with little cubes or stones called calculi, which is where we get the word calculus and calculate.